That's always a good thing, right? Before we get started, do you guys have any questions from what we talked about last night, or do you have any specific questions about power factor correction before we get started? Nope. All right, let's launch into it. Okay, who can tell me what is the whole goal behind power factor correction?
Improving the power quality.
Improving the power quality. Okay. Yeah, I'll accept that. Um, what exactly about the power quality are we improving?
We try to be as close to real power as possible, reduce the amount of reactive,
Perfect. And what does that help us do?
reduce losses in general.
Reduce losses. Okay. Remember that some impedances do require reactive power, especially motors. But for the most case, since we pay for apparent power, right?
Yep.
We're actually paying for any unused power that doesn't actually do any work. So let's look at a standard power triangle. So when we get an electrical bill at the end of every month, what we're paying for is our apparent power magnitude in volt amps. And if you remember from some of the basic definitions of power, the only power that can do any active work, that can actually translate electrical energy to some kind of physical work, that's what we call active or real power. And that's going to be this P value down below. So if our S magnitude is the length of our hypotenuse on our power triangle, then the amount of power is equal to the length of this horizontal component down below. And we know that if we write complex power in rectangular form, showing it as the sum of both real active power and reactive power, the reason why we call this real power is because this is the real component of S when we express it in rectangular. Just like we can call reactive power imaginary power because it's the imaginary component of S when we express it in rectangular. So in other words, imaginary because it's being multiplied by J, and real because it's not. So one of the most important things is just being familiar with the language, because a lot of times the problem, it's not going to tell you P equals this, S equals this, Q equals this, solve for whatever. It's going to tell you something along the lines of the reactive power and the real power is this, and then solve for the apparent power or find the power factor if such. So it's really important to make sure that we can tell these terms apart, because one of the ways they're going to test you is by making sure you are familiar with the definitions enough to set up the problems. So the last one we didn't talk about in the triangle here, we know this is Q. This is our reactive power in volt amp reactance. Of course, P is in watts. So I'm going to draw two triangles really quickly. And what I'm interested in knowing is which one is going to have the better power factor or the more favorable power factor. The triangle on the top or the triangle on the bottom, and why? So remember that power factor, it's always going to be a ratio, right? So the highest value that power factor can be is 1. So power factor is typically going to exist anywhere between 1 and 0. Now, who can tell me off the top of their head what are two ways that we can solve for power factor? How about,
Theta.
go ahead.
Cosine theta.
Cosine theta, perfect. So one way is power factor equals cosine theta. How about, is there another way, a second way we can solve for power factor? So this right here, this comes from the trig function that says cosine theta equals, if we're looking at in terms of reference from this angle, cosine theta is going to equal to P over S, right? So we know if cosine theta is power factor, we also know that P over S also has to equal power factor, right? And kind of like we talked about yesterday, which value do we always expect to be greater, S or P?
S.
Perfect. So since the bigger number is always going to be on the bottom, this also supports that power factor is going to be greatest 1, leading all the way down to 0. So here we have two ways to solve for power factor, right? Cosine theta or P over S. Here's where that ratio comes in. So really, power factor, we're interested in knowing, okay, how much real power in watts, right? This leg down here on the horizontal. How many watts am I getting for every amount of volt amp that I'm paying for? Does that make sense? So do you think we would want to have, this is S, P, and Q, and here is S, P, and Q. So we want to have as many watts per volt amps as possible. Otherwise, we're going to be paying for a lot of total apparent power and not getting a whole lot of work done from watts. So if we compare that to these two triangles on the right, which triangle do you think would better represent a more ideal power factor?
The one on the bottom.
One on the bottom, right? Why is that? Why did you come to that conclusion?
Your cosine of theta is P over S, right? So your angle is lower for the bottom compared to the top.
Exactly. Or if we hold P constant, we can compare these two triangles by saying we can call this Q1 and Q2 and S1 and S2. You'll notice that as Q increases, right, if P stays the same, as Q increases, so does S, doesn't it? So in other words, when we compare these two, we're getting less watts compared to the total number of volt amps. And here, that ratio is going to be better. We're getting more watts per volt amp, right? How about this? So we said that the best power factor, the best value we can have, since power factor equals P over S, the highest value would be 1, right? What conditions have to exist for power factor to equal 1? What do our P and S have to equal?
Each other.
Exactly. PS equal S, S has to equal P, and these two would cancel, right? So if we want to visualize what a system with a power factor of 1 would look like, all we have to do is draw a triangle where P equals to S. What do you think our Q value is going to equal to when we do that? 0. Perfect. So Q is going to equal to 0, right? So what we're left with is a perfectly straight line where we've got P on the bottom and S on the top. Previously, this was the hypotenuse, and this was that real component. So now it's almost like we went from having a triangle like this, and that Q value decreased all the way while P stayed the same until S just about folded on top of P, and they ended up being equal to each other. So power factor equals 1. How about this? If we have a straight horizontal line, what's our angle? 0, okay. Who's got a calculator handy? Remember we said cosine of theta equals power factor? Who can tell me what's the cosine of 0? 1, exactly. So that's another way we can support that hypothesis. So when we look at two extremes of the power factor, we have power factor equals to 1, in which case we have a flat horizontal line, where this would be our complex apparent power, and that's just our apparent power magnitude. And this would equal to P plus J times 0, right? Since P equals to S. So the other extreme example would be what? Since power factor, it can be as high as 1 and as low as 0. What's the other extreme example? Power factor equals 0, right? Okay. So if power factor again equals to P over S, or cosine theta, what conditions do we need that would make this equal to 0?
P equals 0?
P equals to 0, yep. What else? How about, couldn't we solve by taking the inverse cosine of 0? Anybody have a calculator handy?
90 degrees.
Exactly, 90 degrees. So this time around, before I even draw that triangle, what is Q and S going to equal? How about this? So we know P equals to 0, right? So if I've got a phasor diagram like this, I know I'm not going in the x direction at all, right? Because that's our P value. And I know my angle is 90 degrees. So what would a triangle look like that has both an angle of 90 degrees and this horizontal component of P equals to 0?
Slide upward.
Yeah, exactly. So essentially this time around, all we're doing is, if we start out with what that basic power triangle looked like, before, you'll notice that S folded on top of P because Q went to 0. This time around, P is going to equal to 0, right? And we're going to fold all the way up in this direction. So now we literally have a straight line to where our P equals 0, right? That would be, it would be that horizontal component if we had it. We know that this is our apparent power complex vector. Here's our apparent power magnitude. What would this be? P equals to 0, so our P value, it's shrinking all the way to here. And it's pretty much bringing with it Q, right? Q is going to increase until it equals to S. So wouldn't our magnitude of our apparent power have to equal to Q in order to get a straight line with an angle of 90 degrees? Everyone agree? Okay. So for the worst case power factor, to get that 0, our Q value has to equal our S magnitude, and our S magnitude has to equal to Q. Very similar to what we had on the best case power factor. Best case power factor, because for every dollar that we're spending on our apparent power, we're getting watts, right? We're getting 1 for 1. And down here, this is worst case, because for every dollar that we're spending on that total power, on that complex power, we're getting 0 watts. Essentially, we're paying for nothing. Does that make sense? So whenever we talk about power factor correction, we're usually looking to see how we can improve our power factor. In other words, we want to go either from a worst case or somewhere in the middle, and we want to approach as close as possible to a straight, flat, horizontal line to our P equals S. So let's think about this. Let's say I've got 40 volt 3-phase system, right? This is a system bus. We'll say it's a motor control center. And I've got a total amount of motor loads such that the load it draws is going to be a total of 50 volt amps at an angle of 30 degrees. So that's our load. So if we draw this out, we've got 50 volt amps up top, right? That's our magnitude of S. We've got a theta of 30 degrees. Who can tell me how much reactive power that motor is consuming?
I'm going to use the tangent expression.
Tangent expression, sure. Help me out. How would we do that?
Sorry, sine, not tangent. It's opposite of the hypotenuse.
Hang on one sec. I'm just going to adjust my mic a little bit. Okay, go ahead. How would we do that?
Yeah, I was just going to say sine of 30 is going to be Q over S.
Yep. Okay, so sine of 30 degrees equals Q over S. Perfect. So go ahead and let me know what you get for Q when we have 50, let's call that kVA. Let's make that a little more realistic. So we've got 50 kVA times sine of 30 degrees.
Uh, 25 kVA.
25 kVA, okay. Go ahead and let me know what you get for P. Try P equals to that same S magnitude times cosine 30.
43.30.
43.30. And that's, what's my unit there?
kW.
kW, perfect. Okay. So if we're spending, say we're spending $10 per kilowatt hour. So we're spending a total of 10 times, we'll call that kVA. For every dollar that we spend on that apparent power, we're getting an equivalent horsepower outage compared to our kilowatt, right? We can use the kW to horsepower output.
Mm-hmm.
Horsepower is our mechanical energy. Kilowatt is our electrical energy. So we're buying our kVAs, and then it's the amount of kW that's actually doing any work, right? It's a fan, it's ventilating a duct, it's an agitator motor mixing some kind of big slurry, or it's a conveyor motor, right? So if I asked you to improve our power factor, would we need to increase this Q or decrease that Q?
Decrease.
Decrease, exactly. So really quick, someone tell me, what's the power factor of this motor? You can do cosine of 30, or you can do 43.3 kW over 50 kVA.
0.867 or 0.87.
0.87?
Yeah.
So that's pretty good. Typically, in the real world, you're going to see typically around 0.8 something is generally considered pretty good. So what if I asked you to, and I'm going to change my color to red. What if I said, instead of 0.87, we have to figure out a way to improve that power factor? I want to get it to 0.95. How do we do that? How do we go from a power factor of 0.87 to 0.95? And I'll give you a hint. Remember that this right here, that's the load of the motor. Our P value is not going to change. It's going to pull as much kilowatts as whatever is connected to it. And of course, it's really drawing a total complex power, but that's largely dependent on how much energy is being set up in the stator. But you can assume that P is not going to change, right? We talked about earlier, if we want to improve power factor, we can raise or lower Q depending on what we're trying to do. So how about this? How do we find 0.87 equals to power factor? What do we do?
S divided by B.
S divided by P, sure. So we said, okay, power factor equals, is it S divided by P or P divided by S?
Oh, P divided by S, sorry.
Perfect, no problem. And remember, the easy way to remember, we know power factor is a decimal, right? We know it can never be bigger than 1. And we know that S is always going to be bigger than P, unless if it's equal to it. So we know we got to put the bigger number on the bottom. All right, so we know P, we know S, we found our power factor. Now we know our power factor, we know our P, right? That P is going to say constant. In other words, in order to decrease that Q, we can only do that if we hold P constant and we shrink our S, right? That would drag this Q, or I'm sorry, that would drag it down, right? It would keep P the same, but this S value would literally kind of start to fold in that way. Our angle would start to decrease, right? So we say we want to go from a 0.87 power factor to a 0.95. Okay, let's try this. Let's try finding the apparent power magnitude. So we could say that would equal, if we use the same P value, 43.3 kW over the power factor we want to go to. So I'm going to go ahead and punch that in. Let me know how many volt amps you get.
.5 kVAR. Oh, 0.6.
45.6?
Yeah.
And is the unit kVAR or is the unit kVA and why?
I thought it was kVAR, but...
Remember, what are we solving for when we do this?
Oh, yeah, kVA.
Got it? Okay,
Correct.
Good. All right, so I'm going to go ahead and redraw our triangle. So in essence, what we're doing right now, we're pretending that this motor has a different power factor, right? So we're going to say, okay, we know that it's still going to be 43.3 kW. Now we have an apparent power magnitude of 45.6 kVA. So in other words, our S magnitude it's now getting closer to our P value, isn't it? Right? We held P constant and we brought this in. So we went from 50 kVA up here down to 45.6, which is a lot closer to the 43.3 for P. Does everyone see that? Now, another thing I'd like, someone tell me what angle is our apparent power when we're operating at this desired power factor of 0.95. What's my angle?
You could do the cos theta 43.3 over 45.6.
Sure. Go ahead and punch it in. Let me know what you get.
Yep.
You could do that, or if you just solved for your S and that's still in your calculator, you can hit the inverse button and then multiply it by your existing P. That'd also be probably a quicker way to do it.
So get 18.275, so 18.28 degrees.
Say it one more time. 18 what?
18.28.
18.28. We'll say 18.3 degrees. How about that?
Yep.
Okay, so perfect. So the only difference between the power triangle up here in the black and the red is the black is what it's currently operating at, right? Since we said this had a angle of 30. So this was power factor at 0.87. Here's that same motor and that same system as if it was operating at a 0.95 power factor. So what would we have to change to go?
I had a quick question.
Sure.
For the theta,
Yes.
can we use cosine inverse power factor, or would that not work?
Of course. How about try it?
Okay.
Let me know what you did. Try the inverse cosine of our 0.95. Let me know what you get.
18.19.
18.19. All right, so someone was a little off rounding, but it's more or less the same. Go ahead, while you're doing that, go ahead and do our 43.3 kW over our new S, which was 45.6 kVA.
Um, 1.6.
1.6. We should expect to see the same angle.
Oh, did I?
Do you have
I
a,
put the wrong.
remember power factor is a decimal. We always want that bigger number on the bottom. Don't let that's one of those things that'll rob you from getting it wrong.
0.95.
0.95?
Yeah.
0.95. Right. So that's how you got the power factor. Okay. So good. So that's how, right. And then you go from the power factor to the angle. Perfect. Did that answer your question?
Yep.
Okay.
Thank you.
No problem. So let's think about this. We have, what's the difference between these two triangles? And you know what? I'm going to scroll down here. We're going to redraw these just a little bit. It'll be a lot easier to demonstrate this point. So we've got our old angle here, our old power triangle here, the power triangle that we're trying to get to. I'm just going to move this over. Okay, so the new value was P equals to 43.3 kW, which is the same. And then we found the S magnitude was 45.6 kVA. And we know we have an angle of 18.3 degrees. And the existing was, we know we have the same value for P. That was 43.3 kW. That's our P. We had a bigger magnitude of our apparent power, right? Because it was less efficient. So it was 50 kVA. And we said our angle was 30 degrees. And our Q, we found it to be 25 kVA. So 25 kVA, that's our Q. So this is where we started. And this is where we're trying to get to, right? Because this is power factor equals 0.95. And this, of course, is power factor 0.87. That's that same motor. He's just operating in a better power factor in this condition compared to this condition. So let's think about this for a second. How do we get from that initial power triangle in black to the one we want to get to in red? Any ideas? And I'll give you a really big hint. What's the one variable on the right that's missing?
Q.
Q. How do we improve or worsen power factor? What variable do we have to change? If our P stays the same, how do we get S closer to P?
Reducing R.
Reducing R?
No. Never mind.
You're on the right track, but it's not R.
Or reducing Q, right?
Right, reducing Q, right? Q's got to go down. In other words, in order to go, so our P equals to P, right? These two are equal. 43.3 kW, 43.3 kW. Here, our S is less. It's 45.6 kVA. Over here, it's greater, right? So in order to hold our P value constant, we've got to reduce that Q, don't we? That's the only way we can lower that angle, right? You see the only difference between these two triangles is one has a less angle. It's a smaller angle, which results in a smaller apparent power magnitude, which is going to result in a decreased Q, right? Because remember, since we're improving that power factor is getting closer to 1. We started at 0.87, now it's increasing to 0.95. And we said that the best power factor condition we can ever hope to get is when we have a straight line, when Q is essentially 0. So in this example, we lowered Q until it equals 0, got a perfect power factor of unity. So in this case, we know if we want to get from a 0.87 power factor for that motor, we got to lower Q, right? So how do we find out how much do we have to lower Q by?
Solve for Q.
Solve for Q. Perfect. Thank you. All right. How do we solve for Q over here? There's a couple of different ways. We can use a trig function with the angle. We can use the square of the sides since we know the other two magnitudes. Someone help me out. How do we do this? We got two different ways.
You can use the Pythagoras theorem.
Sure. Okay. So what's that? That's S equals the square
minus S square.
Yep. So we're going to solve that for Q. So we get Q is going to equal to the square root of our apparent power squared minus our real power squared. So go ahead, someone tell me what this Q is equal to.
$14.29.
14.29. I'm just going to say 14.3. And go ahead, what are the units for that?
kVAR.
kVAR. Good job. So quick way, how do we know we're going in the right direction? Let's compare it to this Q. This Q was 25 kVA. We know we had to increase it to end up at the better power factor, right? This Q's less, so that looks good. All right.
Zach, your units would be kVAR, right? 25.
Yep, correct. Thank you. Let me fix that. kVAR. Perfect. Okay, so this is the Q value, or kVAR that we started. This is the Q value, the kVAR that we want to get to. So how do we find out how much we got to reduce them by? Can't we just subtract them? So let's look at this. So that new Q value was 14.3, right? So I'm going to say that's right about here. 14.3 kvar. I'm going to call that Q new. And we'll call this Q old. So in essence, we want to find that difference, don't we? Right? So we can say, okay, pretty easy. 25 kvar minus 14.3 kvar. What does that give us?
10.7.
10.7 kvar. Perfect. So, back to the original question. If we want to decrease that power triangle for our desired power factor of 0.95, but we have to keep P constant, we're just going to reduce this Q. What was it? By how much? 19?
Oh, 10.7?
10.7? Yep, 10.7. Okay. And then here's an easy way to remember our units. Since we're decreasing our Q, so from here to here is 25 kvar, we're going to reduce it by 10.7. So we know our polarity has to equal to what? Negative, right? So I'm going to go ahead and make this a negative. So in other words, I'm going to copy this again really quick. In other words, this system right here that we started with, right, that was our motor. That was operating at 50 kVA at an angle of 30 degrees, and we said it was three-phase, 480 volts. If we want to get to that power factor of 0.95, I've got to subtract 10.7 kvar. From that system. Does that make sense to everyone?
Yep.
Good. How about that? Let's see. All right. Now, instead of one motor, we've got two. So we're going to stick with that same motor and just add a new one to it. So this is still a three-phase 480 volt bus. This is that same 50 kVA at 30 degree motor. And we'll say this is a 65 kVA at an angle of 25 degrees. What if I asked you to find the overall power factor of this system? Any takers? How about this? Really quick, just because I'm curious. Who can tell me the power factor of motor 1, the one we just worked?
.87.
Okay. How about this one over here, motor 2?
.906.
906. I'll say 91. How about that? Cosine. Yep. Quick check. Tell me, just by looking at these two loads, the complex loads, how do we know that this one was going to have a better power factor before we even took the cosine of that angle?
It's the angle.
Right. This angle's smaller, isn't it?
Yep.
So this angle's smaller, we know that our power factor has got to be better, right? Quick check just to let us know we're on the right path. Okay. So we found the power factor of each of these by doing what? We just did power factor of motor 1 was the cosine of theta 1, and the power factor of motor 2 was the cosine of theta 2. Right? How about this? We've got one power triangle that looks like this. We've got another power triangle that looks like this. What happens if we add these two? Can't we say this is equal to S1 plus S2?
Okay.
So we can say, okay, that's easy. I know how to do that. That's 50 kVA at an angle of 30 plus 65 kVA at an angle of 25. Who's got a calculator that can crunch that out without having to convert to rectangular?
Uh, 114.8 or 0.9. Sorry.
It's all right.
kVA to the angle 27.2.
All right. So this, what we just did right here, we said our total power, right, equals this. So go ahead and tell me what our total power factor is of that system. You said 27.2 degrees?
Yeah.
Okay.
0.89.
Great. So we know the total power factor of that system is 0.89. How about this? What's a quick check that we can tell by looking at this that we know this power factor is in the right ballpark?
It's between the two.
Perfect. It's between the two, right? Motor 1 on the left has the worst power factor. Motor 2's got an improved power factor, so we know they're going to equal out. Great. So really, these guys are drawing a current, right? We'll say that's I1 and I2. And if this bus was fed from a single feeder, that would be our combined I equals I1 plus I2. Does everyone agree since they're in parallel? Essentially, we did the same thing. We said we're drawing a complex load of S1 and S2. And if you remember, really, if we know our current and our impedance, we're going to find that power. So we can say our total S is going to be S1 plus S2. And then once we know that total S, if we express it in polar form, then all we have to do is say, okay, what's the cosine of that angle, right? Here's one way people mess up. What if someone said, okay, I found the power factor of the first one by doing cosine 30, found the power factor of the second one by doing cosine 25, so I'm just going to do cosine of 30 degrees plus 25 degrees. Big no-no, right? Because remember, even though we punched this in our calculator down here, what our calculator actually did, our calculator converted that to P1 plus J Q1 and P2 plus J Q2. And then it took the sum of the reals and it took the sum of the imaginaries or the Q's. And then it converted that to polar. So we can't just straight add the angles. How about this? I've got another really good example. Really quick, right off the bat, a great theory question. Are these induction or synchronous motors? Most likely, are they induction or synchronous? What's the biggest difference between an induction motor and a synchronous motor?
The conversion mechanism.
Yeah. Synchronous motors, you got an excited rotor, don't you?
Yeah.
If you overexcite that rotor, it's going to operate as a leading machine. If you underexcite that rotor, it's going to operate as a lagging machine. How about an induction motor? Can we run in power factor control?
No.
No. Induction motor, is it going to be a leading or lagging load?
Lagging.
Lagging. Perfect. So are these leading or lagging?
Leading.
Why is that?
Actually lagging. Sorry,
Lagging. Good. Good job.
Your power factor angle is positive.
Yeah. Perfect. Our power factor angle or our apparent power angle is positive. So we know these are these are lagging, so they're most likely going to be induction motors, right? They could be synchronous, but typically it's a lot cheaper just to send a little bit more current through that rotor and excite it just enough so that you get pretty much a power factor of 1. You're actually going to save money by putting a little more DC current on that electromagnet. So that's going to bring me into my next example. Here's our bus. If I had 3 motors, could we find the overall power factor of that system? Easy, right? Just like that last example. Since these are all in parallel, we just add them up.
Mm-hmm.
How about this? I've got a good one. I've got a single phase motor. We'll say he's 240 volts. He's running at not the best power factor. He's got 0.7 power factor. Someone tell me how to get to the complex power for that motor. We'll say that he's drawing a total of 12 amps.
we calculate the power and then use the P over S equation?
Sure. We can use P over S, or there might be an easier way since we already have the power factor. How about this? We'll do it both ways. That way we can verify that it works out. Okay, so start me off. How do we find the apparent power?
Cosine inverse.
That would give us our angle. Let's just start with our volt amps first.
Yeah.
So how do we find the apparent power of this motor? What do we know?
12 amps.
Current and voltage.
Great, okay. So who remembers the apparent power formula?
Single phase, right?
Yep. We said it yesterday. VI, okay. Is it just S equals to VI?
Conjugate.
Okay. So if there's a conjugate here, that means there's an angle on my current, right? Which means that's a complex number.
Mm-hmm.
Okay. Problem, we don't know the angle of our current or of our voltage, do we? So how about this? Can't we just use the magnitudes to just solve for the magnitude of power? Would there be anything wrong with that? Could we say that the complex power would be the magnitude at our angle, where we can get our angle from our power factor? See that?
Mm.
So we could say our magnitude of power would equal our voltage, 240 volts, times what's our current?
12 amps.
12 amps. Someone go ahead and knock that out in the calculator. Let me know what you get. Then tell me what the units are.
2880 volt amps.
2880 volt amps. Okay. Do we know our angle yet? No, right? Someone go ahead and find that angle for me. How do we find that angle?
$45.57.
Yep, 45.57. I'm going to say 45.6. How about, I've got a three-phase motor. Someone give me a three-phase voltage.
477.
477. I saw that eye roll. Okay, we'll go with it. 477 volts, three-phase. All right. Give me the apparent power. Just the magnitude. It doesn't matter.
We don't have a current, right?
No, we're gonna solve for current.
Oh, okay.
How about 30? 30 kVA. And I'm gonna say that this is a leading power factor of 0.65. What's my current? How about what formula?
S is equal to, yeah,
Go
S
ahead,
is equal
yep.
to V. Sorry, S is equal to VI.
To VI, all right.
Yep, VI conjugate.
VI conjugate, okay. And is this a complex number or are these magnitudes?
Just use magnitudes for now.
What's that?
Magnitudes.
Magnitudes. If they're magnitudes, we're not going to have our conjugate, right?
No angle. Yep.
Okay, perfect. All right, so we can solve for current, right? We know our S, we know our V. Solve for our current. So I'm going to say that magnitude of our current is going to equal S over V. Does everyone agree? So we've got 30 kVA over our 477 three-phase voltage. Does that look right to anybody? We're missing something.
Oh, three-phase.
Three-phase. There you go. What are we missing?
Three?
Three.
Oh, square root of 3.
Square root of 3. All right. Where does it go?
477 over.
Yeah, down there.
Let's look at this really quick. So our single-phase formula is going to be the phase voltage times the conjugate of the phase current. Three-phase power is always going to equal to 3 times our single-phase power, right? That's the definition to go from three-phase to single-phase power. How about this? So I say three-phase power equals 3 times, I'm going to plug in my phase values. Now, regardless if it's a delta or if it's a Y, when we convert all 3 of these, because is this my phase or is this my line current?
Line.
Line. All right. Is this my phase or line voltage? Line. All right. So we got to go from phase to line values, right? Now, if it's a delta, my phase voltage equals my line voltage, but my line current equals square root 3 times my phase current, right? And if it's a Y, my line voltage equals square root 3 times my phase voltage, and my currents are one and the same. So it doesn't matter if we're going to, if it's a Y or delta, we know that we're going to have 3 times we're going to have 3 times VL IL conjugate divided by the square root 3, right? Does everyone see where we got that? If it's a delta, then this doesn't matter exactly. So a lot of people get hung up as a Y or as a delta. That square root 3 multiplier is still going to act the same way. So now, can't I say that? What if I multiply by the square root of 3 over the square root of 3? I can do that, right? That's multiplying by the square root, or that's multiplying by 1, essentially. All right? So now I've got, when these 2 on the bottom multiply, what do we get?
3.
So my 3-phase formula, when I use my line values, I've got that square root 3, don't I? And like this problem, we have to work with the magnitudes. We're going to get the angle from the power factor since we don't know the angle of current or voltage. I can solve for the magnitude of 3-phase power by taking the magnitude of my line voltage, the magnitude of my line current, and we don't care about the conjugate because there's no angle to make negative anyways, right? So that's why we always use that square root of 3 for 3-phase power. So down here, if I want to solve for my line current, that means this has to be our total 3-phase power, which we know it is because it's a 3-phase system, and our line voltage times our square root of 3. So go ahead, someone find 30 kVA divided by the square root of 3 times 477. Let me know what you get. I'm going to do it right there with you.
$36.3.
Great, me too. What's the unit?
Amps.
Great. All right. Now then, we got one thing left. So we've got a magnitude and an angle. How do I find my angle?
Lagging power factor.
Leading or lagging?
Lagging because that was leading.
So the leading or lagging, that's never going to change. The angles between S and I will always be opposite, but it's still going to be referred to leading or lagging.
Oh, okay.
So we know a leading power factor. Let's draw this power triangle really quick. So we've got our magnitude is 30 kVA. Our angle is what? Someone punch in that angle for me, please. Don't worry about positive or negative just yet. Just find the angle of a 0.65 power factor.
$49.5.
49.5, perfect. So if we were to draw this, this would be our p-value, right? It's a synchronous leading machine. Are we going to have a positive Q or a negative Q?
Negative.
Negative Q, okay. So then that automatically tells us, it's a good way to remember that our angle has to be
Negative.
negative. Perfect. So we've got negative 49.5 degrees, 30 kVA. Now, when we draw our current and phasor diagram, the first thing to remember is we always use our phase values. Almost always. Because this angle, it doesn't come from the difference of our line values. That angle is coming from the difference from our phase values. And that's a really important distinction. So because we use a conjugate, bam, that conjugate right there. Remember we talked about how we almost always use a reference when our phase voltage is 0? So let's say this right here would be our phase voltage. Who can tell me what the phase voltage is? You don't have to do the math. Just let me know that you are on the same page. It would be 477 volts divided by
Square root 3.
square root 3. This would be our phase current, which would be, if this was a Y system, it would be equal to 36.3 amps, right? So this angle right here, oh, got that backwards. Our phase current would be up here. This angle would still be the same as this angle, right?
Mm-hmm.
We would have, I'm going to say theta I equals, this time a positive 49.5 degrees, and that's right here. So we know that I'm going to say theta phase current is going to equal to the negative apparent power angle. So who can tell me what's my angle for this current that we just found to be 36.3?
49.5.
49.5 degrees. Perfect. Does everyone see how we got that? Good. Do we got any questions? All right. We just about covered everything I wanted to cover. We're just about to hit an hour and a half. This problem, I'm not going to lie, this is bugging the crap out of me because I know I'm doing something really stupid and I hate it when that happens. And I was trying to just work it out on the fly. I'm gonna figure out what I did wrong, and I'm probably gonna cut this out of the video that I upload. But I will. Go ahead.
I think since you only have 2, I know it may not work with 3. I think you can just take the average of the 2 angles.
The average of the 2 angles. But remember,
average of the 2 cosines of the angle.
Average of the 2 cosines. I don't think that's going to work out the same way, but I will try it. It's something really simple. I'm just having a hard time because I'm live right now. But I will work this out on my own, and I will update the notes and get that to you. And I probably will cut that part out of the video. Do you guys have any questions related to anything that we talked about?
As long as when you solve it, we get it too.
No, yeah, I will make sure to, when I get that. I'm probably gonna do it either tonight or tomorrow because that really bugs me. Do any of you guys have any issues with power factor? Any questions?
Just a quick question, Zach, are these the typical kind of problems we will expect on the real exam, or would they ask for, something a little bit more challenging or perhaps easier?
So a standard power factor question is going to be some variation of what we covered. A classic one will be you've got the individual motors or you got the individual loads. Find the total system. Classic power factor correction 101 is how do I improve my power factor? That was one of the first ones we talked about, how we had to decrease that Q, right? I'm glad you mentioned that. Here's one thing that you do see from time to time. So I'm going to pretend like we just went through one of those problems, right? Better triangle. How about this? Say to go from our old power factor to our new power factor, let's pretend like we had to decrease our Q by a total of 15 kVAR. Okay? Let's just pretend like we got all the way up to that step. And then let's say that it's a three-phase system. What if I told you that you have capacitors available in 5 kVAR increments? Really easy peasy question, but it helps to go over it once or twice. How many capacitors would you need to improve that power factor by 15 kVAR?
3.
You just add them. Just like when we were working those transformers and we were adding the sum of the individual apparent power to get the equivalent of the three-phase transformer. Same thing. You just add them. Be familiar with that. How about this? If I've got a capacitor, is this a plus JX or a minus JX?
Minus. J.
Minus. Perfect. How can you tell?
It's usually 1 over.
Yep.
Because it reduces the Qs.
Perfect. That's what I was looking for. We know it reduces the Q value and it improves our power factor, right? And it's going to make our power factor get closer to 1. So let's look at this really quick too. I'm glad, this is actually a really good point. I'm glad you brought it up. This is a phasor diagram for volt amps. Actually, so our triangle, we have P's on the bottom. That's our horizontal. Q is our vertical. And here would be our S vector. So if this is a complex apparent power phasor diagram, we know that over here to the right would be positive P, wouldn't it? Over here on the left would be negative P, right? Up here on the top, what would this be? This would be positive Q, which makes this negative Q. Remember, anytime we're looking at a system, like a generator, if it's supplying power, it's going to have a minus apparent power, isn't it? Essentially, it's negative because that power is leaving. Those volt amps are leaving the generator and entering the system, right? If I have a complex impedance of Z hat equals R plus JX and we've got a complex current going through it, the power for this impedance is going to be positive S, right? Because it's taking volt amps, right? It's consuming volt amps. Does that make sense? It's a fish, like sometimes they'll call this a sink, and sometimes they'll call this, you've heard this a bunch, a source. So if it's negative, it's leaving the subject that you're looking at, and if it's positive, it's being taken by that element. Does that make sense? So when we talk about capacitors in effect, they act as reactive generators, don't they? So if I draw a capacitor would be how about that? Right? Minus Jx. J tells us it's on the vertical axis. X tells us it's on the negative vertical axis. How about if I had something in this quadrant? If I had a plus P and a plus Q, would that be a source or a load? I've got a positive P and a positive Q. Is that
Load.
Load. Great. Am I leading, or is that load leading or lagging? Positive P, positive Q. Remember, all of our... Go ahead. Let's
Lagging.
Perfect. How can you tell?
Because it's positive angle for the S. Where S would be.
Bingo. Everyone see that? So that would be something like that. How about that? Now I've got something. Let me draw a little better. Okay. How about, what's this? So now let's break it down. We got plus P, right? We're consuming watts, aren't we? But we are delivering Qs. We're delivering reactive power. Could this be a overexcited synchronous motor? A motor that would consume watts but still improve the power factor of the system? Would that then be a leading load? Right? We've got a minus Q, but a positive P, don't we? Does everyone agree with that?
Positive P because it's in the it's on the x-axis. Positive.
Positive P. So this is our P axis is the horizontal axis. So anything right?
Right.
And we can also say for reactive power, we've got, how about that? Does that look good to everybody? Okay. Now, how about this? We already said this was a lagging load. We said this was a leading load. What's on this side? So our vertical axis is Q, right? Our horizontal axis is P. So this side has positive P, right? This side has negative P. If I have something with negative P, is it a load or is it a source?
Source.
Bingo. So how about this? If I'm up here now, let's look at what we got. I've got a positive Q and a negative P. Is this a source or a load?
Source.
How can we tell?
Negative P.
It's delivering watts, right?
Yep.
But I've got a positive Q. Is that a leading or a lagging load? Careful.
Lagging.
Careful. Let's look at that. That means we've got some kind of source, a generator. We've got a negative P, so it's sending watts, right? But it's taking in reactive power. That makes sense?
Mm-hmm.
This is a leading source. This is one of the reasons why you can use an induction machine as an induction generator. Here's a great qualitative question. You can use an induction machine as an induction generator, but the reason why they don't do it very often is it's actually going to require VARs to operate. It's going to consume reactive power in order to operate. So how about, let's look.
Zach, is it possible to kind of talk
Sure.
this in terms of current and voltage and determine where the current is leading and lagging?
Sure. We'll do that right after this, and then we'll compare them. So how about last one down here? Is this a source or a load?
Source.
How can we tell?
Minus P.
Minus P. What does minus P mean? What are we doing?
Power's going up.
Delivering or consuming?
Delivering.
Delivering.
Delivery.
All right. What's my Q?
Minus.
Q's negative, right?
Minus.
So am I delivering or consuming Q?
Consuming.
Consuming, right? So this is a lagging source. Think about the easiest way to think about this. If I have a lagging load, I need to supply it with a lagging source, don't I? So where my lagging load has plus P and plus Q, my lagging source has a minus P and minus Q. I got into an argument once with he was our turbo generator master guru. He was a turbo generator engineer. We had these two humongous steam driven turbo generators, and me and him we were just being dumb. We argued over if the generator was lagging or leading or why. It was really stupid. So needless to say, I'll never forget it. All right, so let's talk about current and voltage. All right, really quick, remind me. What's the relationship that we have? Oh, I've been trying to figure out how to get rid of that bar. Great. What's the relationship we have between our theta S and our theta I? So what's the relationship between so right here, this is our phasor diagram, right? Our apparent power phasor diagram. So all of these angles. One thing we didn't point out too, look, that's plus theta. Actually, yeah, this would be plus and minus depending on what we go. But so this is all theta S. If we want to look at current and voltage, what's the relationship? How do we go from theta S to theta I? We mentioned it briefly tonight, but it wasn't a focal point. It was just kind of one of those quick asides.
It's negative.
Negative. Why is it negative? Someone tell me the apparent power formula.
IV, S equal to IV.
S equals to VI what?
Conjugate.
Conjugate. S equals VI conjugate. Are these magnitudes or complex numbers?
Complex.
Why? How can you tell?
Conjugate.
Right, conjugate. All right. So what does that conjugate do to the angle?
Reverse it.
How about this? Theta S. When we multiply, we add angles, right? So I can say theta S equals to theta V minus theta I. And we like to analyze our vectors when theta V equals 0. So theta S equals minus theta I. And really quick, let's talk about that for 1 second because it'll make what we're about to talk about easier. So here is when theta V equals 0. Let's say theta V equals 0. And we've got a lagging load where theta I equals minus, so we'll say 45 degrees. All right. This is a big question we get asked a lot. What happens when theta V doesn't equal 0? You're going to notice theta S still has to equal, right?
Yeah.
So what would happen if, we'll say theta V, because remember, they're constantly rotating, right? Clockwise or counterclockwise if they're positive or negative. So what about if theta v was 45 degrees?
Theta I is 0.
Yeah, exactly. So what is theta s over here? Minus theta I, right? Because theta v is 0, or theta v minus theta I.
Mm-hmm.
So theta s is positive 45 degrees. Great. What is theta s over here? Still positive 45 degrees, isn't it? It's just a really important distinction to make. We choose to analyze all of our vectors at a moment in time. Remember, they're flying around at 1/1/60th of a second for 60 hertz, right? So that means they're going to go, theta is going to go from 0 to 360 degrees. It's going to do that 60 times a single second. We just choose a momentary snapshot in that time. When theta v equals 0, it just makes all of our relationships easier, because then we can just say that theta s equals minus theta I, which also, believe it or not, equals theta z, the angle of our impedance. All right, so really quick, we're going to compare our phasor diagram. We're going to do exactly what we did for voltage and current. Is this lagging or leading?
Lagging.
How can you're right, and how can you tell?
Your current is lagging. Negative.
All right. How about over here? Our current is not negative. Is this lagging or leading?
Lagging.
Okay, how can you tell? You're right.
Angle from the voltage. V and I.
Because I is still behind.
Yeah.
Right? We're assuming these are positive systems, by the way, and systems are always going to be positive unless they say otherwise. What about this? Trick question. Negative systems, do they rotate? How do they rotate compared to positive?
Clockwise?
Yeah, clockwise. So if this is V and this is I, is this lagging or leading?
Lagging.
Lagging. Oh, leading.
Leading. Bingo. Why is that? Let's look at this. We're now rotating clockwise. So
Now.
gotcha. I is leading V. Careful. So very rarely will you have to work a really in-depth problem that's negative, but a great qualitative system is going to say, they're going to give you a bunch of red herrings, and they're just going to casually drop in there for a negative. So ABC is positive, and all you have to do to change direction is swap any of the two phases. So you could say ACB, you could say BAC. Those are both negative. So a great PE exam question is, they're going to set you up as a trick. They're going to test you. They're going to make sure you know that. If you don't, you're going to end up wasting time trying to calculate something that you don't need to calculate. They're just going to say, hey, is this leading or lagging for a negative system? S equals this, I equals. They're going to give you a bunch of stuff. You're going to think you need to set up some kind of circuit, and then it's like, aha, negative system that's standing out. They're trying to fool me. Okay, so up here, this was for a positive system, too. We're going to go back to our positive system. So this is V and I phasor diagrams. So here's our V. Here's our I. Lagging or leading?
Lagging.
Lagging or leading?
Leading.
Lagging or leading? Trick question, you know the answer.
Yeah. This is, if your S is positive.
Lagging
yeah,
lagging or leading?
Lagging.
Lagging or leading?
Lagging.
Forgot to draw my ass. All that power triangle, for whatever reason, the industry term for power triangle, it's just your apparent power phasor. That's all it is. Lagging or leading?
This one, so if your S is negative,
Leading.
leading.
What if we're just used to seeing it like this, lagging or leading?
Leading.
Load or source down here? Look at this. We're used to seeing them like this, right? Load or source?
Oh, it's load.
Load or source?
Still load.
Load or source?
Load.
Does not want to cooperate. All right, how about this? My current in this single phase circuit is going in this direction. Where's my polarity for my generator? On the voltage?
Plus on the bottom.
Plus on the bottom, yeah.
Plus on the bottom.
Or plus minus. Okay.
Where's my voltage drop across this load? Which one's up here? Plus or minus?
Minus.
Minus? You guys got them both wrong. Come on.
Okay. Flipping it around.
Plus. Really quick. I've got a load that's drawing a current. When it enters, is the voltage drop going to be positive or negative?
Positive.
If I've got a generator that's sending a current, my voltage has got to be positive, right? How about this? These two are in parallel, aren't they? Voltage has to equal, right? If you see a DC, same thing, plus minus, right? So how about this? Let's pull these apart one at a time. So this circuit looks like this. Here's our I. Here's our voltage. Here's our voltage drop. Everyone okay with what I just did? Notice how the polarity of our current. How about this? What was this again? Lagging or leading?
Lagging.
Load or source?
Load. Well, it's voltage, so actually I don't know.
It's load. Let's compare it to this. Since this is a series circuit, our current is equal, isn't it? Right over here. We have the same current circling in the same direction in that loop. Right? Remember when we talked about the difference between positive and negative? Negative is a source because it's sending. Positive is a load or a sink because it's absorbing or consuming. Absorbing, right? We expect our load to draw a current, right? We could almost argue that that's our load in amps, right? So how about this? Source or load?
Source.
Lagging or leading?
Leading.
Try again. Let's look at this really quick.
Okay.
Right? This is, I would be very surprised if you saw this, but knowing the difference between your positive and negative values is the most important in terms of right here what we talked about. This generator is going to be sending watts and Q. This would be a lagging source. Right? Minus P minus Q. All right. Do we have any other questions? I'm going to get off screen share really quick. There we go. All right, guys, it's just about 10:30 here on the East Coast.
Cool.
All right, guys, thanks for joining me. It's been a fun couple of days. I hope you got something out of it. And yeah, if you have any other questions, please just shoot me an email. I'll be happy to reply.
All right. Thanks, Zach.
All right, good night, guys. See you.
Good night.
Good night.